Dear students, in this lecture, we'll discuss the torque slip characteristic of a three-phase induction motor. The torque slip characteristic shows the relationship between the torque and the slip of an induction motor. And as you know that the slip is linearly related to the motor speed, this characteristic can also be called as torque speed characteristic. To obtain the torque speed characteristic, we make use of the Thevenin's theorem as applied to the equivalent circuit of the motor. The equivalent circuit of a three-phase induction motor is shown in figure 1, and we replace the portion of the circuit to the left of the terminal pair AB by its Thevenin equivalent. The resulting circuit is shown in figure 2, in which the Thevenin equivalent of this portion of the circuit is drawn here. The Thevenin equivalent comprises of a Thevenin voltage VE in series with a Thevenin impedance ZE equal to RE plus JXE. The voltage VE will be equal to the open circuit voltage measured between this terminal pair, and we can make use of the voltage divider rule to find this voltage, which will therefore be equal to jx phi divided by the sum of these impedances R1 plus jx1 plus x phi times the input voltage V1. So in this loop we find the voltage across jx phi with this portion of the circuit removed. So it is the open circuit voltage given by this. The Thevenin impedance will be the impedance measured between this terminal pair AB with the rotor circuit removed and with the voltage source V1 short circuited. And therefore we see that when we look towards left from the terminal pair AB, the impedance ZE will be given by the parallel combination of JX phi and R1 plus JX1. Therefore ZE, which is equal to RE plus JXE, is the parallel combination which will be given by JX phi times R1 plus jx1 divided by R1 plus jx1 plus x phi. In an induction machine, R1, the stator resistance, is smaller than the stator leakage reactance x1, which in turn is quite small as compared to the magnetizing reactance x phi. And therefore, the sum of x1 and x phi will be very large compared to R1, and hence in these two equations in the denominator, R1 can be neglected compared to x1 plus x phi, and therefore with R1 neglected, these two equations can be simplified as VE will become x phi divided by x1 plus x phi times V1, and similarly ZE will be equal to R1 x phi divided by x1 plus x phi plus j x1 x phi divided by x1 plus x phi. Hence, the resistive component of the Thevenin impedance will be given by R1 x phi divided by x1 plus x phi, and the reactive component Xe will be equal to x1 x phi divided by x1 plus x phi. And as far as the sum of x1 and x phi is concerned, it's known as self-reactance of the stator. Now, if we refer to figure 2, we can write an expression for the rotor current I2 prime. Here, I2 prime will be given by VE divided by the impedance of this loop, which will be equal to RE plus R2 prime by S plus J times XE plus X2 prime. And therefore, let's write the expression for the rotor current. Here, I2 prime will be VE divided by RE plus R2 prime by S plus J times XE plus X2 prime. Now, the torque developed is given by Pg by omega s. We have already derived this expression, and Pg in turn is given by 3 times I2 prime square R2 prime by s. This portion here represents the air gap power per phase, multiplied by 3 is the total air gap power, divided by omega s. And therefore, substituting for the magnitude of the rotor current from this expression, we can write torque as 3 upon omega s into, then I2 prime square will be given by this VE square divided by RE plus R2 prime by S whole square plus XE plus X2 prime whole square into R2 by S. This we have written here. So this portion is the square of the rotor current here, and this equation represents the variation of the torque with Silp. And if we plot torque as a function of Silp, we get what is known as the torque Silp characteristic. If we multiply the numerator and denominator of equation 8 by s square, we can write torque Silp equation also as this: 3 upon omega s into VE square into R2 prime into S divided by SRE plus R2 prime whole square plus S square times XE plus X2 prime whole square. Now we can see that if we calculate the torque at synchronous speed, the value of Silp is equal to 0, the torque is equal to 0. We know that in an induction machine the torque produced at synchronous speed is equal to 0 because there is no relative motion between the rotating magnetic field and the rotor. And then if we substitute s equal to 1 in this expression, we get a finite non-zero value of the torque, and this corresponds to the rotor being standstill, and therefore is known as the starting torque, which can be represented by TEST. This figure shows a plot of equation 8 or 9 and is the torque Silp characteristic. It is seen that the torque Silp characteristic has been plotted for value of Silp from -1 up to 2, and the Silp increases as we move towards left. We can see that a Silp equal to 1 corresponds to a speed. We can label the horizontal axis in terms of speed also, and corresponding to a Silp of 1, the speed will be equal to 0, and corresponding to a Silp equal to 0, the speed is ns, and as we go on increasing the speed, the Silp will be negative, and corresponding to -1 Silp, the speed will be twice ns. Similarly, on this side, if the motor is rotated in the opposite direction of the rotating magnetic field, we see that the speed will be negative, and the Silp will be greater than 1, corresponding to a Silp of 2. Therefore, the speed is minus ns. This figure shows the typical shape of the torque Silp characteristic, and the operation of the machine for different values of Silp can be divided into 3 modes of operation. The first mode corresponds to the value of Silp between 0 and 1 and is known as the motoring mode. The second mode corresponds to value of Silp S greater than 1 on this side and is known as the braking mode. And the third mode of operation corresponds to a value of Silp lesser than 0 on this side and is known as the generating mode. So we see that the motoring mode corresponds to a value of Silp between 0 and 1, and we see that the machine rotates in the direction of the rotating magnetic field, and the torque is developed in the direction of the rotating magnetic field, and it is this torque developed, electromagnetic torque developed, which causes the motor to rotate in the direction of the rotating magnetic field, and hence it's a normal motoring mode. The braking mode corresponds to a Silp greater than 1, and it therefore means that the machine rotates in opposite direction of the rotating magnetic field. But as we see that the torque is still positive, meaning thereby that the torque is developed in the direction of the rotating magnetic field, and hence the developed torque opposes the motion of the rotor, and therefore this mode of operation is used for electrically stopping a motor. And to stop a motor, therefore what is done while the motor is rotating and we want to stop the motor, we interchange any two leads of the supply lines, and because of this the direction of the rotating magnetic field gets reversed. But the motor is rotating in the same direction, and therefore the reversal of the direction of the rotating magnetic field will cause a torque in the opposite direction, which will decelerate the motor, and ultimately the motor will come to standstill. But what must be done is, as the motor stops, the mains must be disconnected, because if the mains are still kept on, the motor will start rotating in the opposite direction. Therefore, as soon as the motor comes to halt, this mains must be disconnected. The third mode of operation is the generating mode, which corresponds to a value of Silp s less than 0. This means that the uh, machine must be running in the direction of the rotating magnetic field at a speed greater than synchronous speed. And in this case, as we can see that the torque is negative, and therefore it is developed in a direction opposed to the direction of the rotating magnetic field. Here also the developed torque opposes the motion, and hence to keep the machine rotating, it must be run by means of an external prime mover while the machine is connected to the mains. So as the machine is connected to the mains and it is run by an external prime mover at a speed greater than synchronous speed, what happens, the machine supplies power back to the mains. So the mechanical power supplied by the prime mover is converted to an equivalent electrical power and is supplied back to the mains. And we make use of the induction generators for wind power generation. For the normal power plants, the generator used is a synchronous generator, but for wind power generation, induction generators are preferred. This is because the wind speed is fluctuating, and the rotor speed will also therefore be changing with the changing wind speed. And if we use a synchronous generator instead of an induction generator, it will generate power at variable frequencies. But this is not the problem with the induction generators. An induction generator will keep supplying power satisfactorily to the grid at the frequency of the grid, even if the rotor speed is changing. But a synchronous generator used with variable frequencies cannot operate satisfactorily, because it will generate voltage with a variable frequency at variable rotor speeds. Now let's discuss the motoring mode of operation in a little more detail. We have seen that the torque versus Silp characteristic in the motoring mode varies. It has a typical variation as shown in this figure. We see that at a Silp equal to 1, which corresponds to an R equal to 0, the motor is stands still. There is a finite non-zero value of the torque, which is known as the starting torque, represented by TEST. And at Silp equal to 0, which corresponds to synchronous speed, the torque developed is 0. And for the other values of Silp between 0 and 1, the torque has a variation as shown in this figure. It must be noted that for low values of Silp, which are in this region, the torque increases almost linearly with the Silp. So the torque is proportional to the Silp. Therefore, as the Silp increases, the torque also increases linearly with the Silp. But for large values of Silp, which are in this range, the torque is inversely proportional to the Silp. As it's quite obvious, as the Silp increases, the torque reduces. Now, since the torque varies directly with the Silp for low values of Silp, and it varies inversely with for high values of Silp, there must be a maximum value of the torque at a particular value of Silp, and this value of Silp has been denoted by SMT. It is the Silp corresponding to the maximum torque, TEM. Now it is clear that in the torque slip characteristic in this region, with increasing slip, the torque is also increasing. In other words, with decreasing speed, the torque is increasing in this region. And it is only this region which is the stable region of operation. The motor normally operates in this region. The other region where the torque increases with increasing speed, on this side, if we move towards right, the speed is increasing, the torque increases with increasing speed, and this region is the unstable region of operation. To understand this, let's consider that the motor is in equilibrium at a point A, and it operates on this portion of the torque speed characteristic. By equilibrium, we mean that the developed electromagnetically developed torque Te will be equal to the opposing torque, which will be the load torque. So the load torque is equal to the developed torque, and the motor therefore will be operating in equilibrium at point A at a particular speed. Now, suppose that there is a small increment of load on the motor. That means the load torque has been increased. The initial response of the increased load torque will be to decelerate the motor a little bit, and because of deceleration, what happens, the speed of the motor will decrease a little bit, and as the motor speed decreases, the operating point will shift to the left. That means on this characteristic it will move downwards, and as the operating point moves downwards, what happens, it means that with decreasing speed, the developed torque has also decreased. We had basically increased the load, but the developed torque has decreased, because of which the difference of the torques will be more, and hence the motor will decelerate more and more, and ultimately it will come to standstill. Now, if we consider the motor to be operating in this region, say for example at point B in equilibrium, it means that the developed torque will be equal to the load torque at a particular speed. Now, if there is a small increment of load torque, the initial response will be a decrease in speed, and therefore the operating point will have to shift towards left. Therefore, on this characteristic, the operating point will move upwards. Therefore, since the load has been increased, the operating point is also moving upwards, and the developed torque is also increasing. Therefore, as the developed torque becomes equal to the load torque, the motor will be operating stably at a point which is higher than point B. And if we go on increasing the load torque, the developed torque will also go on increasing, and the operating point will also go on shifting upwards on this characteristic. And if we apply a load load torque which is equal to TEM, we'll see that the operating point will shift to this peak. And if we try to put more load than TEM, what will happen is the speed will again decrease, but with decreasing speed, uh, the torque developed will decrease, and therefore instead of operating stably at some point, the machine will come to a standstill. It means that if we try to put a load which is greater than the developed torque TEM, the motor cannot supply this load and the motor will come to standstill, and hence because of this reason TEM, the maximum torque, is also known as the breakdown torque. So we see that the portion of the characteristic where the torque increases with speed is the unstable region of operation, and the portion of the characteristic where the torque decreases with increase in speed is the stable region of operation. So the motor normally operates in this region. And one more thing that you should remember is that the design of the motor is such that the slope of the characteristic in this region is quite large. It means that the change in speed for a wide variation of torque is quite small, and we have already said that the motor normally operates at a value of Silp which is just 2 to 4%, and therefore from no load to full load the change in speed of an induction motor is not much, and as such an induction motor is treated as a constant speed motor practically. Now let's proceed to derive an expression for the maximum torque developed. We know that the torque, electromagnetic torque developed, is equal to Pg by omega s, where Pg is the air gap power. And since the motor is operated from a constant frequency source, the number of poles is also constant. Omega s, the synchronous speed, is also constant. Therefore it means that the torque will vary in direct proportion with the air gap power, and the torque developed will be maximum when the air gap power is maximum. And we can make use of this fact to determine the value of the maximum torque developed by applying maximum power transfer theorem to the equivalent circuit. We know that the air gap power in the equivalent circuit is represented by means of this resistor R2 prime by S, and therefore maximum power, air gap power, will correspond to the maximum power delivered to the resistance R2 prime by S. Now for AC circuits we know the maximum power transfer theorem when the load is resistive. For a resistive load the maximum power will be transferred when the load resistance has a value equal to the magnitude of the internal impedance. This is the internal impedance, and when this R2 prime by S is equal to the magnitude of this internal impedance, maximum power will be transferred to this. So applying the maximum power transfer theorem to the equivalent circuit, maximum power will be delivered to R2 prime by S when R2 prime by SMT, we replace S by SMT because now S will correspond to the maximum power, when it is really equal to the magnitude of internal impedance, which is equal to Re square plus Xe plus X2 prime whole square. And from this we get the value of SMT, Silp corresponding to maximum torque, as R2 prime divided by square root of Re square plus Xe plus X2 prime whole square, or this can also be written as R2 prime divided by under root of Re square plus X square, where X is equal to Xe plus X2 prime. Now since we have found the Silp corresponding to maximum torque, if we substitute the value of the Silp in the torque equation, we'll get the maximum torque developed. So TEM will be equal to TE calculated for S equal to SMT, and we have the expression for the torque which has already been derived, and Here we'll, for the sake of simplicity, we'll represent 3 VE square by omega s by kt. This equation therefore can be written in a simpler form as kt divided by re plus r2 prime by s whole square plus x square times r2 prime by s, and hence the maximum torque TEM will be given by TEM will be equal to KT divided by RE plus, now for maximum torque we know R2 prime by SMT is equal to under root RE square plus x square whole square plus, here we have x square, and this again R2 prime by S will be equal to under root of RE square plus x square, and then we'll open this square here and we'll simplify this expression to get the expression for the maximum torque developed. Here TEM will be equal to KT upon 2 times RE plus under root of RE square plus x square. So we'll close here. In the next lecture, we'll discuss the effect of rotor resistance on the torque Silp characteristic. Thank you.